Is that Japanese or is it a?
Japanese.
It's Japanese, yeah.
You used to like catch bugs. Yeah,
Satoshi Iwata.
And that's like where you got the idea.
Oh, wait.
That's pretty cool.
No, that was the.
I don't think it's good.
Yeah.
Yeah, it is.
Whenever I see him, he's got like all the pictures of him.
He made like 8
Isn't like
million.
super print.
All right. So hopefully it doesn't crash consistently because let's hope. Okay. Okay, that's good. Got into Moodle. Get to this class. Okay, so I just want to clarify that sometimes Moodle will schedule classes because it's because I reset the class at the beginning of each semester, so it's recycling homework assignments from previous semesters, and it's using the timing between the beginning of the semester and the time I assign those particular homework assignment to program that into this semester. So sometimes it would have homework assignments that it will say due, but it's not quite assigned yet. Okay, just want to kind of point it out. We are already starting to talk about functions and relations. We are mostly done with functions, and this is a function homework. I don't remember assigning the function homework. I remember there's a quiz that I assigned last week, but not this particular function homework. Is that right? Okay. So I'm going to assign it today, which means you have a week to work on it. Okay. So we'll go take a quick look at the homework assignment. And let's see, where is my... Oh, this is an assessment. And here's another homework here. So I think I assigned this one, but not the other one. So this one was assigned. Did I assign it or not? No? No? Okay. Okay, so I will assign both of them because we have now covered all the topics for functions. So I'm going to change the timing here to, it's already due on the 16th. So that's correct. I think that is the correct date. Okay, so we'll keep this due date on the 16th. Let me just double check. The 16th is exactly 1 week from today, so that's good. Today is the 9th. Yes? 7th. Oh, the year's wrong, that's fine. Okay, now it makes more sense. So today is the 7th, and it's going to be due on the 14th at 9 o'clock. And this one has the appearance of a quiz, and you are only allowed 1 attempt. But you can take as long as you want. Once you open the quiz, you can take as long as you want to complete the quiz. So once again, yeah, go ahead.
Does that mean you can leave it and come back to it? Or?
Yes, you can come back to it.
Okay.
Moodle allows you to start a quiz, log out, sign in from another computer, and continue with the quiz.
Okay.
So as long as you don't click the button that says submit all and finish, you'll be fine. But once you click that and confirm, it'll ask you to confirm one more time. Once you confirm that, then you cannot have any additional attempts. Okay? So this one is really just testing whether you understand the functions, injectiveness, bijectiveness, and surjectiveness, those type of concepts. And then there's another homework assignment called functions, and we're going to work on this one too. So I will have it assigned, and then we'll come back and talk about what it is, how to get it done. So let me make sure the due date is set correctly. So it's set to today, but I never really assigned it yet, so we'll make it the same due date as the other one, which is on the 14th. So you have 1 week to work on this, and the due time is going to be 9 o'clock in the morning, so right at the beginning of this class. So what I'll do is I'm going to display this one, because this one may require just a little bit more explanation. There are 4 parts to it, so make sure you finish all 4 parts to this particular homework assignment. So each one has about the same format, independent to all other questions. In other words, your answer to the question number 1 does not have to be the same thing that you set up for question number 2. So you basically pick 2 digits from your student ID as the domain X. Now, I'm assuming that you have at least 2 distinct digits in your student ID. If you so happen to have the student ID of 111, 1111, let me know, and I'll arrange something for you. But most students do not have that student ID. Most students have at least 3 distinct digits. So once again, if your student ID just so happens to have 1 single digit, repeating 7 times, let me know and we'll work out something. Otherwise, we'll just pick any 2 digits. Any 2 is fine. And then you can pick any number of letters from your last name as the codomain Y. Okay. And once again, if your last name has only 2 letters and it becomes difficult to do some of these homework assignments, let me know, and then you can include maybe your first name or something else. Okay. So if you run into difficulty with these restrictions, let me know. But the bottom line is I want you to define a function f, okay, that maps from the set x to the set y such that it is not injective and not surjective for question number 1. For the second one, it is injective and not surjective. For question number 3, it is not injective but surjective. And then for the last one, as you might guess, it is bijective. Yep.
So you said we can pick different numbers and letters each question?
Yes.
Okay.
Mm-hmm. Yep. So they are all kind of independent. All right. So as an example, okay, this is my potential answer. I'm not saying this is the correct answer for the first question, okay? I'm just saying that this is the way it works out. You have to state what is set x, you have to state what is set y, and then you have to also specify how elements in the domain are mapped to elements in the codomain. So is that okay? Does everybody understand the format of your answer? Now it doesn't have to be done using LaTeX. This one you are free to use just the HTML editor. Just curly braces, parentheses are fine because we don't have any actual math symbols in this case. Is that okay? Are there any questions about the 2 homework assignments that are due in a week? No questions? Okay, go ahead.
Is there one due tonight at 5?
Not anymore. We just changed it.
Oh, that was this one?
I think that was this one. Okay. And then the quiz is also going to be due next week.
Oh,
the so-called quiz, but it's not really a quiz because you have the entire week to work on it.
Okay.
Okay. And I have Mickey here to talk about the student club. Yes?
Yeah.
Okay. Okay. Before we go any further, I have some bad news for you because you are not enrolled in enough units. They won't let you become president of the student club.
Really?
Right.
Okay.
So do you want to take more units?
Yeah.
Okay. So we'll deal with it. We'll deal with this later. But I just want to remind you that I got a letter from the people who are in charge of student clubs.
What class? What other class? 362. Do you have anything open in that?
Probably.
Okay. Cool.
All right.
All right. Hi guys. Sorry to interrupt your class. As Zach said, my name is Mickey, and at least right now, until things get worked out, I'm the president of the Computer Science Club. Some of you guys may not be aware that we have a Computer Science Club here on campus, but we actually do. We've had one for a number of years. And in the past, it was a conflicting schedule for some, myself included. But this semester, we have something a little unique. We actually have a club open 4 days a week. Before it was only 2, now we have 4. We actually have a Monday, Wednesday from 11 to 1, and we have Tuesday, Thursday from noon to 3 o'clock, and it's located in 152D. So when you go into the computer lab, you hang quick left, it's that door on the left over there. In the past, we've had projects dealing with the Arduino bots. A couple semesters ago, we had somebody working on a game using the Unreal Engine. This year, per TAC's suggestion, we're going to wait to see how many people are interested in being in the computer club, the computer science club, and we're going to ask them what they would like to work on as a project going on this semester. So again, I'm not going to take up too much of your time. Just want to let you guys know that we do have a computer science club here on campus, and Monday, Tuesday, Wednesday, and Thursday we are open in the computer lab. A lot of times you just kind of hang out and do homework, and someone comes complaining about, I don't understand how to do this homework. Well, let me see if we can help you out with that. So that's kind of the things we have going on right now. Yes.
What are your Tuesday and Thursday hours again?
Tuesday, Thursdays are noon to 3. and Monday and Wednesday is 11 to 1. Potentially that could be adjusted. One of the other people in the club, the vice president, a guy named Kevin, he's not available on Tuesday, Thursday, but he really wanted to be a part of it, so he petitioned to get the room a couple extra days, so we actually do have it for the Monday and Wednesday classes as well. Yes?
Did you say the location of it?
Yeah, it's right on the other side of this building. 152D, which is the computer lab. As soon as you walk in, and quick left. There's a door on the left, got glass windows and stuff. You see a couple guys in there hanging out, arguing about physics and other stuff. Any other questions? All right, again, my name is Mickey. I'll get in touch with TAC as far as contact information if I say I'm still going to be the president, but in any case, again, I just want to let you guys know we do have a club on campus, and if you're interested, just swing on by 152D, Monday through Thursday.
All right.
Thank you, TAC.
Well, thank you, Mickey.
Yes, I'll get with you about the other stuff.
Okay.
Okay, thanks, TAC.
Sure.
I'll see you at 10:30.
And there it is. Yeah, I felt proud about the whole thing too. So.
Okay, thanks, guys.
So I apologize for those of you who had to go to the original classroom and then find your way over here, because I forgot to mention that the classroom has changed. In fact, I went to the other classroom too, and go like, who's there in that classroom? I thought I'm the first class in the whole day. No, and then I remember, oh, that's right, I switched classroom with Greg, and he's the teacher in the other classroom right now. He teaches business law. Really cool guy, retired lawyer working for corporations. That's the kind of lawyer that you want to become if you want to become a lawyer. These are the lawyers who never have to go to court. Because they just work for corporations, they get all the paperwork done. They are strategists, not tactical operators like certain types of lawyers. All right. So the student club thing is really a good opportunity. Since you're in 440, you're almost done with many of your classes already. The student club still has a lot of value because every year we organize at least 2 barbecue events. The tri-tips are great, okay? But besides the tri-tip, we usually invite, or people self-invite themselves. They crash the party. These are people who have transferred to UC Davis for the most part, and also Sac State, because they're local enough. So most of the time they will come back and just kind of hang out. So you can get a feel of what it is like as a transfer student from the other side. You can hear stories. You can also ask them for advice, and stuff like that. So it's a great opportunity to connect to people who are like 1 or 2 years ahead of you, who have already transferred to a 4-year university, so that you know what to expect when you transfer. And you can ask them for tips like, okay, I'm planning to transfer, what should I do? How should I prioritize stuff and whatnot? Okay, so it's a great opportunity for people to hang out and talk about that sort of thing. And then it's also fun too, depending on what you guys want to do or what the members of the club want to do. We can invite industry people, to talk about what it is like in industry. We can talk about other fun topics like how to hack computers and whatnot. So anyway, getting back to our homework assignment here. So this one is due next week. If you get a head start, not a problem. Okay, if you otherwise you have 1 week to work on this. All right. So are there any questions, general questions about functions for this class, in the context of this class? No questions about functions? All right. I think we talked about, this is the next one, composition of functions, which is related to what we already covered last week. And you can see this is a really, really short slide because it doesn't have to be long. The composition of functions is simply saying that you can make a function out of multiple functions. You can apply the result of one function on, as an argument to another function. So in this case, I have an example. The example is if you look at f of x that is defined as 3x plus 5, okay? It is a composite of 2 functions. The first function is we can define g of x as 3x, and then we can define another function h of x as x plus 5. So when you look at these two functions, g and h, okay, the composite of these two can now become the same as function f, because now I can define function f of x as function h applied to the function g of x, or the result of g of x. And that becomes, if you expand it, it becomes g of x plus 5, because h is just adding 5. But then g itself is 3 times, so the end result is 3x plus 5. Are there questions about the concept of having a composite of functions, or using composite of functions in treating it as one single function? It's very similar, if not exactly the same, as these similar concepts in calculus. Okay, because in calculus you have to know the composite function thing to do your derivations, right? I still remember enough to mention that. So the way we write it down is, in this particular case, f is a composite of g and h. We apply g first and then h. The symbol in between is like a little circle. It simply means the composite operator. Now the nice thing about the composite function is if both component functions g and h in this case are bijective, then f is also automatically bijective. In fact, the inverse function of f is the inverse function of h compositing with the inverse function of g. And you have to see that the ordering is opposite, because in this case we apply g first and then h, but in the reverse case we have to apply the inverse of h first and then the inverse of g. And this has to do with the last in first out, or stack ordering of things, because you have to inverse the last operation first, and that's why it looks like that. So are there any questions about the composite of functions, or composition of functions? Yep.
Which kind of convention are we using? Because I know that there are 2 different conventions for which goes first. So when you say G circle H, is it going to be like apply G first and then apply H, or
yes,
apply H first and then?
It's applying G first. So we are nesting G inside H.
Oh, okay. Because in other math classes I've had it the other way too. So.
The other way? Well, I mean, it's if this is how we define it, we can just stick with this one, or we can change it. I mean, it's just a convention. Whichever way, we can look it up.
It's G of H. That's read G of H.
Okay.
So G goes into H on that notation.
So this is correct?
Yeah, that's G of H.
That's G of H. Okay.
Algebra. Like
That's what-
abstract algebra.
So.
No. Because like when you write matrix multiplication, then you say G H.
But this is not matrix multiplication.
But people do it that way in at least in the abstract algebra class I took. People have done it that way. But
All right. We'll ask the most authoritative resource here.
yeah.
Wiki, it's right there.
It's the same thing.
No, it's the actually the opposite thing.
Yeah, it is.
Yeah, this is reverse to what I said. This one has f
Yeah.
applied on top of g.
F of G would mean that G would have to go first.
Yeah, this one is opposite to what I described.
Yeah.
And we'll
There's
check
different
one more.
conventions, only different forms of mathematics, like.
Okay, so this one, yep, I got it reversed. I stand corrected.
Yeah, 'cause if you're doing G of F, you have to resolve F first.
Alrighty, so I got it wrong. So I'm gonna change it. So in this case, we have H and then G over here. And I think that's the only place I have that notation. Okay, are we good?
You
Can
have
you
to
also
switch
change
G
the
Huh?
to the inverse.
Oh, right, the inverse has to be
First
switched.
paragraph.
Oh, this one here, yep. So what I need to do is look for that little symbol, the circ symbol. go. That's one. Oh, that's one here. I missed that one. And the inverse has to be opposite. So this is H, and that is G. There we go. Okay, double checking. So the circle is good, circle is good, this one's good too. So I think we are square. Okay, all right. Okay, so we talked about the application of functions already, I think. Okay, the composition we kind of skipped. Okay, well, this is an example. We haven't really talked about this one. This is an example that we talked about at the beginning of the class. You know, how do we express that an array is sorted? Okay, and by using a bijective function, we can actually, it's easier to express it. All right. So the problem that we are having, if I use my document camera, I can show you exactly what the problem is, because we're having a problem with the vocabulary to express that. But now that we know what functions are and we know properties of functions like bijection, we finally have the way to deal with that. So I'm hoping that this got it fixed. So let's see. Yep. I specified the permissions or the group ownership when I started up the computer, so it doesn't have a problem with that anymore. Okay. And there we go. Okay, so the problem with expression sorting is we have to make sure that if you start with certain numbers like 3, 1, 2, 4, okay, you have to make sure that these numbers still exist in the output, right? So in this case, we need 1 to go here, we need 2 to go here, we need a 3 to go here, and then a 4 to go here. Okay? In other words, if you compare the elements as a starting point and you compare the elements as the result of sorting, they have to be the same values, okay? You cannot have more than one instances of one value compared to the beginning. You cannot lose some of the values. You cannot change the values. So the problem was, we were not able to express this earlier in the semester. But now that we have functions, we can actually express it, okay? So what we'll do is we're going to look at sorting as two things. One is the precondition, which basically states what are the conditions that we start off with, and one is the postcondition, which states, okay, when everything is done, this is the end result of applying the algorithm. So at the beginning, as the initial condition, what we'll say is for all I as an element of the set, okay, from 0 to the number of elements in the array A minus 1. Okay, this is just my notation. I am borrowing the cardinality operator to also apply to arrays. So bar A bar, in this case, A is an array, but bar A bar means the number of elements in the array. So let me just make it clear that A is an array. Okay. So I'm just saying that for each I, such that I is going from 0 to bar A bar minus 1. In other words, for all legal indexes into this particular array, the following is true. This is the precondition. Okay, so we'll just randomly pick a constant k here and say that k underscore I equals to A in bracket I. Okay, so in this case, the use of the square bracket is has the same meaning in C and C++. It's an indexing operator for arrays. The subscript I, which applies to k, is just a notation to say that yes, we have a certain number of constants. Okay, and then the constants, each constant is tied into a particular value of a particular array element at the beginning of the algorithm. Is that okay? Just a notation. Okay, so we want the final state to say that, okay, now the array A is now sorted. But how do we state that? One part is easy to state. Okay, the part that is easy to state is for all I such that I is an element of 0, this time to bar A bar minus 2, because we want to express the relationship between adjacent elements in the array, not the set, but in the array. So that part is really easy to state because all we have to say is to say a bracket I is less than or equal to a bracket I plus 1. Right? So this basically just says, okay, the array is sorted. It is a sorted array. But the next question is, are we having the same values as the original array? Because that's a big restriction. Because if that is not a restriction, you can just pick the first element of the entire array, copy it throughout the entire array, and you're done. But that's not sorting. Are we okay with that concept? Okay, so the difficulty is how do we relate the values of the array after the sorting algorithm to the values of the array before the sorting algorithm? Before, we were having problem expressing that because we did not have the notion of function. But now that we have the notion of function, then we can say the following. Okay, so we can say this is a requirement. It is important. We need to make sure that that is true. But we also want to make sure something else is true as well. So here's the big and. Okay, so the next thing we want to do is to say there's a function. So that we basically say there exists a function f. Okay, the function f is going to map indexes to indexes. So it's going to map 0 to bar a bar minus 1, which is the set of all valid indexes. And it's going to map it to the same thing, 0 to bar a bar minus 1. In other words, we have a function that maps valid indexes to valid indexes in the array. Doesn't sound very exciting, right? So we're going to express as well. We want to say that f is bijective, okay? Which means it has to be injective and also be surjective at the same time. Now the last part is the most important part. The last part is basically saying for all I in 0 to bar a bar minus 1, the following has to be true. Okay? So this is the magical part. The magical part is we have to be able to apply f. Now which side you apply f does not really matter, but I'm just going to apply to the k side or the constant side. So this time I use k, but the subscript of k is no longer just I, it is f of I, and then I say this is the same thing as a bracket I. This is the most important part. Okay, everything else is just kind of like, those are really useful things, but this is the key. This part here is what does the mapping. Are we okay with that concept? The existence of this function f is only here to make sure that we have a one-to-one mapping from the values of each element in the array from the initial state to the final state. And we make sure that we don't miss anything. How do we make sure we don't miss anything? Which part of this slide says we cannot be missing anything? There's one particular word, and there's only a few words here, but there's one particular word that says, yes, we are not missing anything.
Bijective.
Bijective, exactly. Okay, the word bijective, or the fact that f is bijective, means that we cannot be missing anything. If you started with a particular value k of something, it has to exist in the result. Is that okay? So now we have a way to express it. And once again, this has nothing to do with sorting algorithms at all. It doesn't have anything to do with the time complexity of sorting algorithm. It is only here to state the requirement of a sorting algorithm. How do we express the correct result of a sorting algorithm? Is that okay? But why is this important? I always think, the algorithm itself is important. Well, it is, but this is important as well. Why is that important?
Improve the sorting.
Yep, exactly. And hopefully at some point in time, okay, maybe not in a decade, maybe in a century or so, we can just state the initial state and state the desired final state, and we'll have the computer to figure out the algorithm to solve it. Okay? That might happen in 100 years. And 100 years later, people will say, well, that might happen in another 100 years. All right, so are we good with this slide? The rest of the note on the website is really saying the same thing. It's just, maybe I express it slightly differently, but it really is the same thing. We talked about this part already, the result of assignment operations. It allows us, if a function on the right-hand side of an assignment is bijective, it gives us the ability to reverse trace a program. Given the end result of a particular statement, we can actually work our ways backwards to figure out, okay, if this is the post condition of a statement, then we can work our way back to the precondition of that statement, which is the post condition of the statement before that one. So we can apply this, step by step and work our way back as much as we can. And this is a good, really useful step in debugging. And that's the end of this particular slide. So are there any questions about these two things? Let's think about, remember there are 3 levels of questions. The first level is what, which is basically all the detail. So in this class, the what is going to be, the use of the symbols, for all there exists, the set operations and stuff like that. That's the what. That's the how, that's the how. The what is, okay, but what theorem are we proving using all these, kind of obscure symbols? That's the what. And then the highest level question is the why. Why are we dealing with this? Why is this important? So do we have any questions regarding the why, the highest level portion? Why are functions useful in practical programming terms? No questions? I don't know how to ask the question. Okay. About the other part, how about the other part about how to reverse execute a program? No questions about that? Okay, so we'll just leave this alone for now. But this slide is a good segue, is a good way to transition into relations. And the reason why we have to transition into relations, or why this is a good slide to transition into relations, has to do with this guy over here. You cannot express ordering unless you have an ordering operator. In this case, we use less than or equal to express ordering. And in this particular case, we are able to express ordering between any 2 values, okay, which is really useful. So what we're doing next is to get into the slide of relations. I have extended this particular slide, which is binary relations, a little bit, okay, not a whole lot, just a little bit. So we'll basically start with the notations first, just like we did with functions, and then we'll talk about properties of relations, and then we'll talk about the application of relations, why it is actually useful in computer science. So we'll start with the terminology first, okay? We basically say a relation R over a set X is basically a subset of the Cartesian product X Cartesian product with X. In other words, when you look at a relation, it is like this, okay? In a way, it is kind of like a function, because with a function is a subset of the Cartesian product of the domain and the codomain. In this case, the domain, well, there's no such thing as domain and codomain, but the 2 sets of the Cartesian product, they have to be the same. They cannot be different. In other words, you can only express relation over a particular set, but not over 2 different sets. Is that okay? So that makes it different compared to functions. Okay, you do not have the ability to say, okay, this is my domain and the codomain is different from my domain. That you have to be talking about the same set. If an element X in X relates to another element Y, which is also in X, through R, then we say that we use the notation X, R, Y. Okay. In other words, we basically just say that X relates to Y. That's all we are saying. To indicate that this particular tuple, xy as a tuple, does exist in the set R. And this is kind of redundant. XRY or X relates to Y is true if and only if the tuple xy is an element of R as a relation. All right. So with all of this stuff here, let's talk about certain relations that we are already familiar with. Okay. And I'm going to use the document camera for this purpose, or you can just use a WordPad or mouse pad. But a piece of paper works really well as well. Okay, so if you think about relations in computer science, there are a lot of relations that you use already. Okay, every time you compare numbers, you're using relations because every single comparison operator is a relation. Okay, so every time in your C code, if you have something like this, if x is less than y, then do this block of code. Okay, this is a relation. Okay, it doesn't have an awkward name of r because we just say less than, right? So x is less than y is a relation. So in the case of this particular case, if x equals to 1 and y equals to 5, then x is less than y is true. Which also means that which also means in this case, 1, 5 is an element of this particular relation. You will just say that it's the less than relation. In other words, relation is a set. Every relation is a set of two tuples. Just like with any functions, it is also each element of a function is also a two tuple. That's how we look at things in this class. Are we okay with the concept of what a relation is? Okay. So we're going to switch back to the notes here. There are several properties of relations that we can say something about. Okay. So we're going to forget about this one for now. We'll come back and deal with that later. The first thing we can talk about, or the first thing that we can, as a qualification, is reflexive. We can say whether a relation is reflexive or not. Okay. So in this case, a relation R over a set X is reflexive if and only if the following is true. And the condition that makes a relation reflexive is every element has to relate to itself. Is that okay? Okay, let me check whether you understand the concept or not. If you look at less than, is less than reflexive as a relation?
No.
It's not reflexive because an element or a particular integer value cannot be less than itself. But less than or equal to is reflexive because an element or any integer value is always less than or equal to itself. It's okay? Is that okay? All right. So let's look at the next one. The next one is symmetric. Now, to us, from the perspective of just the words, reflexive and symmetric seems to be related. Okay, because when you look into a mirror, it's reflecting, and what you see in the mirror is symmetric to what is in real life. But in mathematical terms, they are different. Okay, so let's check out what makes a relation symmetric. The first part is still the same. We use R to denote a relation, and we use the set to X to basically say R is over that particular set. It is symmetric if and only if the following condition is true. So if you look at this condition here, it's saying for all x lowercase x in the set X, for all y in X. Okay. In other words, give me any two elements x, y. Okay. The following has to be true. If x relates to y, then y has to relate to x. That's the condition that makes a relation symmetric. Are we doing okay so far with this? So let me ask you this question. Is less than symmetric? It is not reflexive because, it's not symmetric because 1 is less than 2, but 2 is not less than 1. Okay. How about less than or equal to? Remember, less than or equal to is reflexive, but it is symmetric. It's not. Okay. 1 is less than or equal to 5. But 5 is not less than or equal to 1. So what relation is symmetric? How about not equal to? Not equal to is symmetric, but is not equal to reflexive.
No.
It is not reflexive. Okay, 1 does not equal to 1 is not true. But 1 does not equal to 5. 5 does not equal to 1. It is symmetric and yet not reflexive. So are we okay with these two terms, reflexive versus symmetric? Yep.
Does equal sign work for symmetric?
Yes. Equality is symmetric and reflexive. All right, so let's move on to antisymmetric. Now, antisymmetric is not just saying it is not symmetric, it has certain kind of nuances to it. Antisymmetric means that for all elements x and y in the set that we defined the relation over, this condition, x relates to y and y relates to x, has to imply that x equals to y. In other words, if this is true and this is true, then this has to be true. But you can only have one without the other, then the implication would not work. You can have none, then the relationship does not. Then the implication does not work. Is that okay? Does everybody understand what is antisymmetric? Let's go ahead and recheck the relations that we had seen earlier and see if they are quote unquote antisymmetric. Let's look at let's look at an obvious one first. Then we'll look at a less obvious one. Let's look at less than or equal to. Okay, if r is less than or equal to, does this description fit it? Is it true that if you pick any two elements, if x is less than or equal to y and y is less than or equal to x, then it implies that x and y are exactly the same?
Mm-hmm.
It works, okay? So that's kind of an obvious one. What about equality? X equals y and y equals x implies x equals y. Come on, that's an easy one, right? Okay, what about this one? What about less than? X is less than y and y is less than x implies x equals to y for all elements in the set, x and y. So is less than a relation that is anti-symmetric?
No. I don't think so.
Okay, we'll take a vote first, which does not actually define the correct answer. But how many people think that less than is anti-symmetric? You don't have to raise your hand, you just have to kind of think about it, okay? And I claim that less than is anti-symmetric. Okay? So, okay, so the key to that is this is an implication. Okay? Now, how do we define implication? What is implication? As a Boolean operator, what makes an implication true and what makes an implication false? Okay, so let's go ahead and revisit that because we talked about that a few weeks ago, and because we don't use this definition very often, it's not unusual that we might have forgotten a very crucial part of implication. Now, implication, okay, so let's go ahead and define two independent variables, and we'll call that x and y. So we have two independent variables, x and y, and so that makes it easy to make a truth table because we just have 0, 0, 1, 1 for x, 0, 1, 0, 1 for y, so that's an easy one. Now we go ahead and define the result of x implies y. Now remember, x implies y is not an assertion that x does imply y. It is simply a question. Does x imply y? That really is the question. It's no more different. It's no more an operator than conjunction. Okay, it's just defined by the result here. X implies y. False implies false. Is that true? Now, what is the other way to define implication? Remember that? Not x or y. Okay, so these two are by definition the same. Okay, so if x is false, what would be the result of not x or y? X is false to begin with. Not x is true, true, or whatever it has to be true, right? So we already know the first two rows are true. What about the third row? X is true, which makes not x false. So the only way to make the entire expression true is y. But yet y is also false in this case. So we have false or false, which means the end result is false. The last one is true because even though x is true, which means the negation of x is false, but y is true, so not x or y is still true. So the only way to make implication false is this one. Right? I know it sounds kind of awkward that false implies whatever is true, but that's just how the operator is defined. So let's go back to the notes here. I'm just going to switch back on the screen a little bit here to get back to the note here. So I'll just focus on the part that I was just talking about, which is this part here. Okay? So we look at this expression and say, okay, what exactly does it mean? Well, what it means is this expression is true for the cases where x r y and y r x is false. No questions asked. In other words, if you consider less than, okay, if r is less than, then this part has to be false. X is less than y and y is less than x has to be false for integers, right? Is that okay? But what happens to false implies something? It is always
True.
true. Okay. So if this is false for all possible pairs of elements in X, because in the set of integers, no integer can be both less than and greater than another one at the same time. So that means for all elements, X and Y, in the set of integers, this entire expression, the part that is already highlighted, has to be true. So that makes less than actually anti-symmetric, which is kind of counterintuitive.
Hmm.
Is that, yep?
So the main reason it's antisymmetric is because of the previous example you gave where f can't be both less than y and y can't be less.
It is simply because the first part of implication is false for all pairs of values in integers. Okay, let me highlight that part here. Less than is antisymmetric because this part is always false. No matter which x or y you pick from the set of integers, this part is going to be false.
Okay.
But in the implication, if this part is false, the entire implication is true. So that means this entire thing is actually true for the set of integers when we consider the relation less than. Now, less than is antisymmetric, but so is less than or equal to. Okay. Are we doing okay so far with this? Yes? Yep.
Less than or equal to, because both of those will be true.
Or equal to?
You said less than or equal to is antisymmetric, would it be because both the conditions would be true?
For less than, it is antisymmetric, but less than or equal to is antisymmetric as well.
Okay.
Because for less than or equal to, you can actually find elements where this condition is true, but that's only when x and y are exactly the same. So that makes it true as well. Yep.
Can you explain why making the implication false makes the whole statement true?
Okay, that one is a. You mean this one here? The definition of implication. Yes.
So is this like if magic then Santa Claus must be true?
Okay. So let's look at this from a different perspective, okay? Because from the math or kind of abstract perspective, it is a little bit hard to fathom. But if I switch it to something that has to do with money and refunding, and then you're paying me and stuff like that, you guys may pay more attention or understand it a little better because you want to get your money back. Okay, so what I'm going to do is I will say your tag charges you $100 for, quote in quotes, a pearl of wisdom. Okay. All right. There's no such thing as well. Okay. When people talk about the pearl of wisdom, a pearl of wisdom, you kind of have to think about what a pearl really is to the clam that made it. Okay. I don't know whether they're called clams or not, but they're soft-bodied animals that make pearls. So what are actually pearls?
Calcium.
It's some kind of irritation that is coated so it's not as irritating anymore. And that's basically what wisdom is. No? You guys are not getting it? You have a bad experience, so you learn from the bad experience and say, okay, it may not be a good idea to touch that when it's hot. Okay? So that's a pearl of wisdom. It comes from irritation. It comes from things that you do not like to begin with. Then you coat it, and it becomes valuable, not to the clam itself. Okay? Has any clam ever been happy and say that, look at my pearls? No. So who appreciates the pearls? Not the clam. It's the people who extract the pearls from the clam, right? The same thing applies to wisdom. The people who actually learn it may not enjoy it, but other people go like and go, wow, this is really cool. Okay. So I'm going to charge you $100 for something. So I would say if the sky is, let's pick a color that is very, very unusual for the sky.
Pierce. Pierce.
How about fuchsia? How do you spell fuchsia?
CHS.
Huh?
CHS.
CHS. Huh?
CH, yeah.
F.
U.
Uh-huh.
CHSIA.
Fuchsia. Oh. That doesn't look like fuchsia to me.
Are you sure it's not SCH?
Yeah.
Okay, now I have to find out. Fuchsia. Okay, that should be good enough.
Okay.
No, it is fuchsia. All right. Must be a French word then. Okay, so getting back to my one here. So if the sky is fuchsia, then the whole class will fail the final. Okay. Well, you paid $100. I better give you something, right? All right. So this is the statement. Okay. I say, okay, this is true. I claim that it is true. Okay. But remember, the condition itself, if the sky is fuchsia, then the whole class will fail the final, is not an assertion. Okay. It is just a claim that can be either true or false. Is that part okay? I'm not telling you, this is not a fact. Okay, it's not established as a fact. It is just a statement that you paid $100 for. Is that okay? So one day you think, okay, I need to buy that calculus book. I'm short, $100. Maybe I can see if I can get that $100 back from TAC. Okay, so you want to see when can I get that money back from TAC? So we have 4 scenarios. The 4 scenarios is a day where you observe the sky, and unfortunately it is not true. It is not fuchsia. The sky is blue, it's black, it's orange, okay, but it's not fuchsia. So, and given that, and at the end of the semester, not the entire class failed the final, okay, a few people passed, can you get your money back? Cannot get your money back. Now, most people think they cannot get the money back because the class, not the entire class, failed the final. So let's check the next condition. You check the sky. The color of the sky is not fuchsia because it's nighttime. It's just black. Okay, and as it turns out, the entire class failed cisp440, the final exam of the 440 class. So in this case, can you get your money back? Is this scenario, is this observation contradicting my statement? No, because my statement never said anything about what would happen if the sky was not fuchsia. Is that making any sense? Mm-hmm. So you cannot get your money back because the statement is still true, because I didn't say anything about what happens when the sky is not fuchsia. Okay?
There's no statement about when you get your money back either.
Sorry?
There's no statement up there about when you get your money back either.
Okay. Fine prints, right? Okay, you can get your 100%, 110% of your money back if TAC is proven wrong. Asterisk, but only in this example. Okay, because that part is important, otherwise I'll be broke very soon. Okay, so the third row says, okay, you observe the sky, it's like, oh look, it's fuchsia, okay? So after taking a picture like everybody else, and then you finally get to the class, and you look at the result of the final exam, and a few people passed, okay? Can you get your money back? Yeah, you can get your money back because the first condition met, and then the second condition is not met. It contradicts to what I said, okay? And then the last one is quite obvious. The sky is fuchsia, and the entire class failed the test, failed the final exam. Can you get your money back? Nope, because it happened just as I predicted. But the key is not the last two rows. The last two rows are very obvious, okay? So these two rows are usually not the problem. The first two rows are the problems with most people because they go like, but how can this be, how can I not get my money back, especially for the second row? Because whether the conditional statement or the implication is true or not is not only dependent on the second part, but it also depends on the first part. Is that okay? So when you look at this truth table here, and when you can get your money back because the statement is false, does that remind you of this? Because they are exactly the same. Okay? Do we have any questions about the meaning of implication? Yep.
Is this because there's no way to know whether or not X implies Y if X is false in the first place?
Well, when we use the word implies, it basically says, if I say X implies Y, it is only relevant when X is true. X implies Y basically says, if X is false, we don't really care. But the way we state we don't really care is that the statement is still true. It is not proven wrong or proven false. Is that okay? Sort of? So there are two ways to proceed at this point if you're kind of thinking about this and go like, well, I'm still not getting it. One is just look at implication as an operator. Okay, this is the way it is defined, and that's basically it. Okay, and of course the second way is to go back to my example and go like, okay, when can I get my money back? Okay, so you're going back to the meaning of the word if. Now, if the word if is defined as implication, then we have been using the wrong keyword in programming all along. Okay, now do not bring this back to Mr. Fox or Damon or Iraj, okay, because they would just go like, tag, what did you tell your class? Okay, so we'll say if X is less than Y, then we'll perform a statement here that states Z equals to 20. Okay, so it has nothing to do with the condition itself. All right, so the question now is, since I use a single word if, it means it's implication, which in this case means X is less than Y as a condition implies that I should take the action Z equals to 20, right? And this is what you have been doing since CISP 300, okay? The use of this word if has been used in that way. Is that okay? But when you map this to the truth table, we're in big trouble, okay? So let me just go ahead and display these two side by side, okay? Because it doesn't say anything about what should happen when X is less than Y is false. Implication does not say anything when the first part is false. So technically speaking, if you have a statement that says if X is less than Y, Z equals to 20, it does not really say anything about what to do when X is less than Y is false. What if X is greater than or equal to Y? Maybe we should go ahead and do the X to Z equals 20, maybe we should not. It doesn't say anything. So if you are to redesign the programming language and choose the keywords correctly, what word would you use to replace if? If and only if, yes, okay, that would be the correct answer, okay? Now, if and only if is really long, and programmers, especially C programmers, do not like long keywords, so you can abbreviate it to IFF, okay? If and only if. So once again, do not bring this back to Iraj or Dave or or Damon, because they are just going to say, Tag, you're nitpicking the words, but it is wrong. Okay, so getting back to our discussion here, okay? So that's why antisymmetric is kind of tricky, okay? Anything that has implication is actually a little bit tricky. Okay, so here we have the last one, which is transitive. Transitive is actually one of the easier ones, but it still has implication. It says for all x in the set, for all y in the set, and for all z in the set, okay? In other words, pick any three things. Can be the same thing. Pick any three things from the set X. And once again, it is using the implication to define what is transitive. If you pick any three things, and this is still true, then the relation is transitive. In other words, if you can show me that x, r, y is true, if you can show me that r, r, z is true, then I automatically know that z, r, z, x, r, z has to be true. They're starting to sound like new model from Acura or Honda. Is that okay? So what if the relation is empty? What if there's nothing in the relation at all? Would that relation still be transitive according to this definition? It is. Okay, so let's go ahead and actually look at an example. Okay, because when we look at these description, I think because this is probably your first or second class that makes use of for all there exists element of that kind of symbol. So that may kind of throw off some people. But if you look at concrete examples, then it would actually be fairly clear why this is actually transitive. So I'm going to define X as a very simple set. Okay, it has two elements, 1, 2. Okay, easy peasy. So that makes X the Cartesian product of X and X to be a fairly easy set. It is just 1, 1, 1, 2, 2, 1, and 2, 2. Now that's just the Cartesian product. This is not the relation. The relation has to be a subset of this Cartesian product. Is that okay? So one way to define the relation is it's just an empty set. Nothing is relating to anything else. Are we doing okay so far? Okay? So unlike functions, relations do not have restrictions. Now functions have a very important restriction where everything in the domain has to map to something in the codomain. You cannot leave anything in the domain unmapped. But in a relation, it can be anything. It can be any subset of the Cartesian product of the set and itself. All right? So that means the empty set is just fine as a relation because there's no such thing as a requirement of they all have to relate to something. So when you look at the empty set, okay, and then you go through the definition that we talked about a little bit earlier, okay, so we still pick three things from X, okay, so you can pick 1, 1, 1, okay, X, Y, and Z are all ones, okay. So when you look at X, Y, Z, all they're all ones, okay, then you go like, does 1 relate to 1? No. So that makes the conjunction automatically false because we don't even need to check the second one. But if the conjunction is false and this is the first part, the left-hand side of an implication, what does that make the implication itself? True or false? It's true. So that means an empty set, an empty relation is automatically transitive. It's really, really not intuitive, but it is. Are we doing okay so far with these definitions? Sort of. Okay. And I'm going to skip, well, equivalence is easy. Equivalence is just a conjunction. If you find a relation that is reflexive, symmetric, and transitive, then it's also called equivalent. Okay, or the relation has the equivalence property. Is that okay? Oh, since we're on this slide, let me ask you, Is an empty relation reflexive?
Yeah.
Let's go back to the definition. Okay, so for something to be reflexive, I need XRX to be true for all elements in X. But an empty relation, nothing relates to anything else, including to itself, so an empty relation is not reflexive. Okay, because this does not involve the use of implication at all. So all the tricks that we talked about with implication does not work on reflexiveness. All right, so after talking about all these abstract terms and how to qualify relations and stuff like that, why do we bother with relations? Why is it so important that we have to understand this in one of the classes in computer science? This sounds like something that mathematicians may be interested in, but not in computer science. So what we're going to do is we are going to look at ordering, okay, because that's the important part. So I'm going to use an example here, and I have no idea of how people rate paintings and art and stuff like that. So, but I'll just use an example. So we'll basically evaluate paintings based on 4 different criteria in this case. We'll look at the creativeness, the initial impact. When you look at a picture, did you get the feeling of wow, okay? But once you hang it on your wall, do you have long-term appreciation of that painting, or after the first impact you go like, oh, for the rest of the ownership of that painting? And then the last one is the demand in the market. Do people want to buy your painting? So I'm just randomly picking 4 things to evaluate a painting. And then for each thing, I have a 1 to 5 star system. Okay, kind of like Amazon. You basically say, yes, this thing is really creative, has a lot of initial impact, but it is kind of empty. Once you hang it in the wall, after a few days, you would kind of go like, well, I don't really like it anymore, and there's no demand whatsoever of this painting in the market. Okay. So now the question is, if you are writing the software for an auction site for paintings, okay, and people say, okay, please sort the available paintings in evaluation, okay, in ratings. What are you going to do? Because you have 4 attributes to each painting, right? And whoever is telling you to complete this website did not tell you how to aggregate the 4 independent criteria into a single number. So how do you say, okay, is this painting better than the other painting? Now you can, go ahead.
Could you use like a weighting system?
But you were not told how to weight it, right? So one thing you can do is to say, if a painting is better than another painting in every single way, it is better. That makes sense, right? It does make sense. So now you have an ordering system that only works for certain paintings. Because what if one is really creative and has a lot of initial impact, but has no long-term appreciation value and no demand whatsoever? And then you have the flip side of another painting where you look at it and go like, no, that doesn't look very creative. It's just a picture of a scene from a little small market that has no initial impact and no creativity. But the more you look at it, the more you appreciate it, because you start to pick out little details of people, sticking their head out of the window, actual action of people selling stuff in the market. And as it turns out, the artist is really famous and has a big demand in the aftermarket. Then how do you compare these 2 paintings? There's no ordering anymore. Okay? So this is a real life situation. Okay. So how does this impact actual programming? For those of you who want to know more about Zen and Taoism, you can click on these. But in C and C++, ordering is very, very important. We need ordering, and not just ordering. We need total ordering, not partial ordering. In other words, we need everything to be comparable to everything else. Not just between certain things. Yes, I can compare these 2, but between those 2, I have no way of actually comparing and tell you the ordering of those 2 items. So we need total ordering. It's because we have built-in functions. Okay, some of you may know the sort template function already. How many people have used this in one of your other classes? How many people are thinking, I wish I knew about this when I was taking CISP for 30 or 400. Okay, but it's just a sort function. Okay, it's a template class or template function, and it does sorting. But it relies on one thing that is really, really crucial because it can sort any objects. It can deal with any type, any class, but it relies on one really important thing. And I'm going to look for dimensioning here. Okay, oh, that's not going to work. Okay, so it depends on the definition of the less than operator. And I'm not sure where it states here. Oh, okay, comparison function, there we go. So you have to supply a comparison function as a function object. In other words, you have to say, okay, how do we define less than? Okay, that's all it needs, okay? Because when it has less than, you can kind of imply the less than or equal to, or greater than or equal to, and equal to. But that's a very big jump, okay? Just because you know how to define less than doesn't automatically mean that you know how to define the other operators, or it implies the other operators. Yep?
Can't you just like overload less than in your class definition?
Yes, you can, and it will make use of it. Okay? So let me give you an example. Remember the painting example. So we have two paintings here. I'm just looking at the evaluation. So one has 2 stars here, 3 stars here, and 4 stars, and 4 stars. Okay? And I have another painting where there's 1 star here, 2, and then 1 here, and then 2 here. Now between these two, you can say, oh, we can easily define the relation between these two. It's that, right? This painting is better than that painting. Not a problem. But when we have another painting over here, and all I need is to have 4 stars here, 1 here, 2 here, and then 3 here, then you can no longer compare this with this, unless you are told how to weigh and come up with a single number out of the 4 different criteria. Does that make any sense? So in this situation, it is called partial ordering because for certain elements, you can compare. The relation does exist. But for certain relations, it does not exist at all. Between this one and this one, you can neither say this nor that. Well, if you cannot say less than or greater than, there's no chance you can define equal to. So as a result, you have a big problem now. Because the sorting algorithm depends on, it implies, okay? Anything that is less than is automatically not greater than or equal to. Anything that is not less than is automatically greater than or equal to. These are assumed by the sorting algorithm. So if you have paintings that are already rated like this, that this is how you define the ordering, the algorithm will still run, but the result of the algorithm is meaningless. Okay? Whatever is the last element in the entire array is not necessarily quote unquote the best, because you cannot even define what is the best. Yep.
You can do like one thing. There are a lot of algorithms that work on cosets that actually run in less than or equal to n log n time, which it can create something which is non-decreasing. So effectively.
But you cannot even define what is decreasing, right?
I mean, you can make it so that if x is less than or equal to y, then y will always appear after x, like later than x.
But what if all the elements in your array are not comparable?
Then there's
Then the order,
like you can't do anything.
then the result of the sorting algorithm is totally useless. But you cannot even tell whether it's useless or not. That's the problem. The only reason why you can tell the result of the sorting algorithm is useless is because you understand the concept of total ordering as opposed to partial ordering. If you have a operator, a relation that's only partial ordering, then you cannot use it in sorting, period. If you know it is total, then you can use it in any sorting algorithm, including everything that is applied in C++. That is the reason why it is important for us to study relations. It's not, well, the mathematical symbols and stuff like that is kind of fun to me, okay, but it doesn't have application. The application has to do with when you are given an assignment at your work to do sorting, you have to first make sure that there is a way to sort or to compare totally, which means everything has to be comparable to everything else. Is that making any sense? Just the why part, okay? Just the highest level of the questions. Is that okay? No questions? Okay. Now, let me check the time here. We still have 2 minutes. So I'm going to switch back to the website here. Check back to my note here. And so it relates to anything that has to do with ranking. And ranking is important, as much as, I do not really like to rank and compare and stuff like that. It is important. Many of you are on your way to a 4-year university. How do the universities decide who to admit in what order? Who is given priority and who is not? There's an ordering, right? They look at the evaluation. This person has a high GPA and not really a whole lot of demonstration of leadership and other stuff, okay, just a really high GPA. Whereas this person has a really kind of okay GPA, it meets the minimum requirement, but this person seems to have, a lot of other activity that is valued by the university. So how do they come up with the actual ranking? They must have some way to come up with a total ordering to do the ranking. Because if you don't have a total ordering, then you end up with a whole bunch of students or applicants who cannot be compared to each other. And if that is the case, then the university can no longer decide, okay, we have a pool of 20 people, but only 5 spots, okay? And they have no way to decide which 5 out of the 20 to admit to the university. So anything that involves ranking, sorting, ordering requires total ordering. And it may seem to make sense that everything is totally ordered, but that's not the case. This is a prime example of why it is not the case. If you need a painting to be better in every single aspect compared to another painting to be called better, then it is possible that you cannot come up with an ordering amongst certain types of paintings. Is that okay or not? All right. So I would focus on the why first, okay, which is kind of bad because I wrote the why as the last part of the slide. So, but as you're studying these notes, kind of think about the application first. Why is this topic important? Then you go back and look at the what and the how, the lower level stuff, the low level, the mechanical aspect of these definitions. But the why is very important. All right. So it is time. Remember the 2 homework assignments already assigned. Okay, there's 1 critical quiz and 1 homework assignment that you have to type something. And I'll see you guys next Monday. Have a nice weekend if I don't see you again.